First, thank Fabian for inviting me. I am really happy to be here. I'm talking about one of my favorite subjects. So, MIR, or Music Information Retrieval for early music documents. In particular, I'm going to focus on the technologies behind the semi-automatic encoding of mensural sources into symbolic scores. So again, this is my new affiliation, the University of Nova Lisboa. But uh, what I am presenting here is mostly my work during my PhD. So I am including my affiliation to McGill University. so uh, what is behind this long title? Technologies behind the semi-automatic encoding of mensural sources into symbolic scores. Um, First, I want to clarify what mensural sources are and what are symbolic scores and why do we want to obtain the symbolic scores from these particular sources. So going into the first question, what are mensural sources? These are music sources, either manuscripts or printed books, written in mensural notation. So of course, the next question would be, what is mensural notation? Um, So it's a notation system using the Middle Ages, late Middle Ages, and the Renaissance for notating polyphonic music. So music where each of the voices, like you can see in there, has their own particular melody. It is the immediate predecessor of our current notation system, the Common Western Music Notation, and as such already has certain similarities. You notate pitch in the same way. You have staff lines, as you can see, and at the very beginning of each of those staves, you can see that you have clefs. So pitch is clearly notated, and in the same way as we notate it nowadays. You already have different note shapes. However, the note shape is not enough to convey the duration of a note in this type of notation. So what do I mean by this? It is common to have the same note even next to each other, and in that case, even with the same pitch, but they will have different durations. So this is the modern transcription of this passage, starting from those two notes. The first note has a ternary value, which they call perfect, and I'm going to talk about later. And the second note has a binary value. So the first note is a dotted half note, so three-quarter notes, ternary value. The second one is just a half note, so it has just a binary value. Another example here with these two semi-briefs, which are those diamond shapes over there. And the first one has a regular quarter note value, but the following one is twice as long. It's a half note. So what is going on? So in mensural notation, the duration depends on two factors. The first one is what we call a mensuration, which is basically the meter of the piece, which can be duple meter or triple meter. In duple meter, the notes have a binary value by default. In triple meter, they have a ternary value by default, which is what was happening in these pieces in this first example. The first brief has a ternary value by default. So what's happening with the next brief? What's going on there? That's when the other concept comes into play, which is the context. In triple meter, the duration of the individual note symbols is not absolute. It's not just that default value, but rather depends on the context. The context refers to the notes preceding or following, and it can change the value of a note. So this piece, I don't know, I am not going to tell you why we know it's in triple meter, but it's in triple meter, and you have the 3/4 here in the time signature to prove it. So it's in triple meter, and that means that all the briefs, all those square notes, are supposed to have a ternary value by default. Um, so again, that's what happened in this particular note. It's a perfecta. Again, what I call perfect is this ternary value. And the other one is not, because the context changed its value. The context refers to that following semi-brief, which magically changed its value from that perfect note into an imperfect one. That's what they call when they lose one bit and becomes an imperfect or binary note. And this is a common modification based on context called imperfection. There are two common modifications that happens because of context in triple meter. The first is imperfection, the other one is alteration. And that's what happened in this second example. This note is a regular, semi-brief is a regular note, and then the other one, the one that follows, it's actually altered. And this alteration means that a note doubles its value. So those are the two kind of modifications. So this is just to give you a perspective of what's happening in mensural notation and the things that we have to deal with when working with it. Pitch is clearly notated. Note shapes do not explicitly convey the value of a note if we're in this triple meter. Their default value is this perfect ternary value, but that can be changed by the context in these two ways: by an imperfection, where the note becomes imperfect or binary, or by an alteration, which makes the note twice as long. So there are rules about when to apply these context-dependent modifications, when to apply imperfection, when to apply alteration, when to apply both of them, which is what's happening in this second example. We have an imperfection at the very beginning, here. This note is imperfecta, and we have an alteration here in the red note, or when to apply none of them. So that's the first part. This is just to tell you, it was like a mensural notation 101, just an introduction. So now that we talk about mensural sources, why do we want to obtain symbolic scores from them, and what are symbolic scores? So usually mensural sources are written in separate parts. So either having the parts in a different area of the page or the book opening, or have them in completely separate books, like part books. What we want is rather to have them in here in this separate parts layout, to obtain them in this kind of layout, in a score layout, where all the notes are vertically aligned. Why would we want that? So there is an advantage on having them in score layout. If you have them in the original layout, you can only see the melodic information for each of the voices. If you have them in a score layout, you can, in addition to see that melodic information, you have access to the vertical sonorities. You can see which notes are being sung at the same time. So that's the advantage of having them as scores. Uh, but we don't want just any score. We want a symbolic score, which is a score that is encoded in a symbolic or machine-readable format, like MEI, which I'm going to mention later. And that has also advantages in itself, because if the machine is able to read the score, it can process it. For example, it can play it back. It can maybe convert it into modern values if you have a script for that, and it can do much more. But of course, to obtain this, we have to deal with the interpretation of the note's duration, with all these imperfections and alterations, and this kind of context-dependent modifications. So now let's move into that we have talked about symbolic scores. Let's move into symbolic formats that we can use to encode this type of notation. So first of all, a symbolic format, in general terms, is a machine-readable format that encodes symbols of a music document. I included music XML because it's like the most common example, and maybe the one that you're most familiar with. You can export it in Finale, Sibelius, MuseScore, and other graphical editors for music notation. Um, it's typically the way that you use it as an interchange format. Maybe you have just Sibelius and you want to pass your file to someone that is using Finale. Of course, you cannot send your file, and because they won't be able to open it. So you can export it to Music XML, and the other person can import it in Finale and actually see the music contained in there. But of course, Music XML and all of these graphical editors are just for common music notation. And we want to use something that has support for mensural notation. So these two are the main formats that have support for mensural notation: MEI and Humdrum. So MEI stands for Music Encoding Initiative. You might have heard about it in this lecture series, or will hear about it later on as well. MEI refers to the scholar community that works on defining the best practices to encode a wide variety of music documents, and also to the format that they are investing their time in creating. So as I said, it can encode a wide variety of music documents, and that includes documents in early music notation. So documents that have nums, also tablature or mensural notation. Um, for the people that are not familiar with MEI, it looks like this, like the example on the right. You basically have tags, and each of these tags represents an element. So in this case, I have three elements in MEI, a beam, and within that, I have other two children elements, which would be these two nodes. And this is representing what is in this image over here. So a beam with two nodes. It follows this kind of hierarchical structure. So this beam element has two child nodes, node elements, and each element can have attributes that define some characteristics for that element. So in this case, the first one has a p name attribute, which represents the pitch name, which would be f. It has an oct attribute for the octave, so it's an f4. That's this particular f over here. The dur for the duration is an eighth note, as you can see in the image, and the standard direction is up. So it's basically just defining characteristics of that particular element. And the next note element, of course, is the same, but the pitch name is C rather than F. And what we're using to render the MEI, so to display the music that is actually encoded in MEI, it's Verovio, which is a C++ library developed by Laurent Pujan. So, as I said, this has support for mensural notation, and you can see it here. So this is the same example that I showed you before. So we have here one of the briefs. As you can see, it has a perfect or ternary value, and here we have another one that has an imperfect value. And they are both encoded in the MEI file. You can see that they have the right pitch and octave, and both of them are brevis. That's the note shape. But the one at the beginning of the passage is imperfecta, dur quality imperfecta, and the one at the end of the passage has dur quality perfecta. So all of that can be encoded in MEI. Similar with what's happening here for the semi-briefs, this one has a regular value, and this one has an altered value, and you can see that in the MEI encoding. This is just dur semi-brevis, and the other one has an additional dur quality attribute that says that it's altered. So one of the formats to encode mensural notation. The other one would be humdrum. So this is a symbolic format defined by spines, so by these columns. Basically, each of these columns is one of the staves that is present in the image. So here you have your notes for the soprano, the notes for the alto, the tenor, and the bass. So if you basically rotate this like 90 degrees, you will have the score that is over here. So the humdrum format for common Western music notation is kern, which you can see here at the very beginning of the file in line 9. This is encoding common music notation because here you have the text that says kern. For mensural notation is mens. The other advantage of humdrum is that you have already a lot of music analysis tools. They can only be used with kern, so with the common music notation, but you have even tools for Renaissance music. You just have to have a modern transcription of the Renaissance piece. So, as I said, support for mensural notation. This is the same passage encoded in MEI like I showed before, and also in humdrum. So you can see it has the same pitches. The first note has C, C to represent the note C in octave 5. And then you have here the other notes that are an octave below, B, A, G, and D. The first letter in each of these entries is basically the note shape. So capital S is for brevis. You can see it in the first and last note. And then lowercase s is for the semi-briefs, so for the diamond shapes. And for all the perfecta, imperfecta, and ultra, you can also encode it there. You can see the characters in color, the I for imperfecta, the plus for ultra, and the P for perfecta. So, two great formats to encode mensural notation. So now that we have covered what mensural sources are, what are symbolic scores, uh, I'm going to focus on a real life example of a project that involves this semi-automatic encoding of mensural sources into symbolic scores, in particular about the MIR technologies. So this is a project that I conducted for my dissertation. The goal was to preserve and increase access to a set of polyphonic querbooks in Guatemala. Why Guatemala? Because that's my my country, so I wanted to apply to those sources. So preserve and increase access to these by using digitization and music encoding technologies. So I obtained permission for a pilot project with a book of masses from Guatemala. And the first stage, of course, was to obtain the digital images because in that case there weren't high resolution color digital images. But that's another topic. We had to even do a DIY or do it yourself book scanner and everything because we didn't have the equipment for that. But again, that's not music information retrieval, that's before. So, what I'm going to focus on is how, from these sources with the different voices, we obtain this MEI score, sorry, with interpreted durations. And again, the idea of these scores is to increase access to the corpus because uh, you can ask Barovia, which I mentioned before, to actually play back the music. If you write a script, you can actually perform automatic transcription of these into modern values because you already have the durations and everything is lined up. So the first will make it accessible to the general public. The second, the automatic transcription into modern values, would make it accessible to modern musicians. And the third point is that, well, this music came to Guatemala from Spain. So you have a lot of concordances with the European sources. So if both are encoded, the European source, the piece in the European source, and you have encoded the piece in the Guatemalan source, you can do comparisons of concordant sources easily using software. So that's also interesting for experts because they don't have to focus their time on transcribing the music into a score, but focus their time in music analysis. So for this project, this was the three-step process. Digitization, of course, is basically photographing the folios, the pages of the manuscripts. Then optical music recognition. So optical music recognition is similar to optical character recognition or OCR. So that's when you have an image of a text document and you use OCR to recognize the text characters in that document. And in this sense, you can make the image machine readable and searchable. So you can do the exact same thing with OMR or optical music recognition. So it will give you a symbolic file, an MEI, sorry, an MEI parts file that encodes the symbols in each of the parts or voices that are in the original manuscript. But as you know, whether dealing with mensural notation and encoding the symbols, just the pitch and the note shape is not enough because of the previous explanation. So to provide the full information regarding the node duration and to obtain the score properly lined up, we also need to encode all the imperfections and alterations. So we need this third step that gives us the score. So this third step is actually consists of two parts. The first one is something that interprets the duration of the notes and aligns them in a score layout. So the automatic voice alignment or automatic scoring up of the parts. And then the other part will be the editorial correction. Because to properly line up the piece, you also need to correct the scribal errors that are kind of messing up the alignment for you. So this part will also correct the errors and encode both readings, the original and the corrected one. So that's the workflow. These are the tools behind the scenes. As I told you, we have to build our own DIY book scanner for this, and I have slides, like extra slides for this if you want to see them, but it's not relevant to this particular talk. But yeah, we built our own book scanner for that particular manuscript. Um, so I'm going to focus on the music information retrieval technologies. So the first one is MuRET. MuRET is the tool that we use for OMR. It's developed in the University of Alicante by David Rizzo. And it has support for optical music recognition of both common music notation and mensural notation, both handwritten and printed. So the interface looks like this. This is the overview interface. You can see all the pages of a particular piece. That's actually from the Guatemalan manuscript. And you have three icons on top of each of these images, and they represent three different interfaces uh, corresponding to each of the steps to complete the OMR process in MuRET. So the first of those interfaces is the document analysis or document segmentation. So this is a common pre-processing stage in OMR. So basically, in document analysis or document segmentation, you segment your documents into the pieces that you will use afterwards. In this particular case, in MuRET, you ask MuRET to automatically detect all the staff regions for you, because those are the regions that have the music symbols that you want to eventually encode. So that's the first interface. The second one, represented by this guitar on the top, if you can see it. This one is where you assign the voices. So, one short note: this step is performed automatically. You ask MuRET to do this for you. It has been trained to do that. This other step, the assignation of the voices, that's a manual step. It's really simple. You basically do a multiple selection of the staff regions and assign them to a particular part, a particular voice. Um, the next um, The next interface, the last one, actually performs two processes that are common in OMR. The first one is the music symbol recognition process. In this case, you select any of the staff regions of the pages, the ones that have already been recognized during the document analysis, so the first stage, and you ask MuRET to recognize the symbols for you. So you ask MuRET to recognize the symbols for you, and it will show you in this middle panel the symbols that it has identified. Um, it basically has two types of information for each of these symbols. The type of symbol, so if it's a G clef, here it looks more like modern notation, so a whole note, a half note, or these kind of things, and the position in the staff where it is, in which line or space it lies. So you have the interface to correct it. You can move the pitch up or down, or select a line or space that the note is lying on. And you can also correct the symbols using this panel on the left. Just going to drink some water. um, okay, so that's the music symbol recognition part. So it tells you the class of symbols that it finds and the position in the staff where they lie, the line or space. And again, you can correct all this information in that interface. The second thing that it does, um, it's the music notation recognition step of OMR. This is another automatic process. So now that you have the classes of symbols and that you have the line or space where it lies, you can basically deduce uh, the pitches, for example, by using the clef that is here. So it's trying to not only recognize the symbol, but also kind of reconstruct the notation. So this is uh, what in MuRET they call the difference between what they say it's an agnostic representation, so something that is agnostic to any meaning of the music symbols, and what they call a semantic representation. So something that already understands a little bit more about music semantics and music structure. So in here you will have information about pitch already. Uh, and you can correct all of this information using this panel on the left. This panel on the left is actually humdrum format. It's MENS, the format that I mentioned you could use for encoding mensural notation. But in this case, I don't know if you will be able to see it, but in this case, it's encoding pitch and note shape, but it is not providing anything about perfect, imperfect, or altered quality. That was not what they wanted to do um, for this interface. If you want to encode that, you will have to manually add the right characters for this in here. So add the P, the I, or the plus sign for all this type of information. So at the end, when you're happy with your results, you can select a couple of pages or the whole piece and export it into MEI. And that's the last stage of any OMR process, which is the music encoding of the piece. So we have the symbols, we have the OMR done. We can move to the third part of this workflow, the one where we get the score. So for this, I use the Measuring Polyphony Editor. This was being developed while I was doing the dissertation. The principal investigator for this project is Professor Karen Desmond. That's her old affiliation, Brandeis University, when she was working on this. Um, Now she's in Maynooth, I think. And the developers of these are actually from McGill. We have Juliette Regenbaugh, the lead developer, and you have me, which I implemented this voice alignment functionality, this interpretation of the note values. And consultants like Laurent Pujan from Perovia, Craig Sapp from Humdrum, and Andrew Hankinson from IIIF. So, the Measuring Polyphony Editor, or MP Editor, looks like this. It can be used with or without OMR. So, the MP editor can be used from scratch by uploading a manuscript and entering all the notes of the piece by typing them in your keyboard. You can load a manuscript from Gallica and Ecodices, I think. Or you can upload an MEI file that has already all the notes encoded for you, like the one we generated with the OMR. And this is the way that we are going to use it, and that I use it for this project. So you have all the symbols coming from the OMR. Again, you're free to enter all these yourselves. Like, you create each of these staff regions and then type in the symbols. But in our case, they come from the OMR file. So let's move to the next step of this editor, which is the score editor. So we continue into the score editor, and that automatically lines up the notes for you in this format. That's the part that I work on. You have some options below to make it more human readable. You can switch to modern clefs, and you can bar by different note values. So here we're barring by the semi-brief. That's how the piece looks when it's barred by the semi-brief. So it shows a little bit better the perfect groupings or the triple meter of the piece. You can update the voice alignment when correcting notes. So you can select notes, you can move them up and down to change the pitch, you can change the note shape, you can insert notes, and every time that I insert a new note, you will see how the voice alignment updates. Here I'm going to insert a dot of division between those meanings here I inserted it, here there's no dot, to change the perfect groupings. So you can do all of these modifications here. And in case you want to record both readings, the original and what you modified, like in case of scribal errors, you can do that by moving into the editorial mode over here. So in that case, you will have whatever was there before and your correction encoded in the MEI file. And when you're happy with that, you can download your MEI score. So this is the general workflow. I use it for encoding these pieces from the particular manuscript. Of course, there was a lot of work that had to be done, for example, for making these two tools that already existed interoperable. So that MuRET, the OMR files that were exported, were actually useful for the Measuring Polyphony project. So we made them so that they follow certain Measuring Polyphony specifications. And I guess you already know this, or you already deduced this. We did that because we wanted to make the process automatic as possible, right? So when we export something in MEI for within MuRET, we can actually obtain the score here if we want, but you will see that that score is not really lined up. You can see here it's not really lining up, and that's because all the perfect, imperfect, and altered values are not encoded. If you want to encode it, again, as I said, you will have to manually enter it here in the MENS file. Um, so we don't want to do that. The OMR is capable of recognizing the symbols, and that's really well done in here. So let's use that advantage, that automatic part. And as you know, you have very nice interface to correct every symbol that is wrong. So let's use that, and then let's export it to the Measuring Polyphony Editor, so that that takes care of the other process that you will have to actually do manually here. So I made a lot of work with the two developers of the tools, of these two tools. So then, of course, you can export that into the MP editor. As soon as you click that, you get transported into the Measuring Polyphony Editor, and you can load the file in here. And as I said, you have all of this information already coming from the OMR. So you are avoiding this manual task of entering all that yourself and just focusing on the automatic task and correcting that. So trying to get the best of both tools in here. So as I said, I work with the developers of these two tools, David Rizzo and Juliet Regenbaugh, to make them as interoperable as possible. So we have a paper on that. The other thing that we did is, so I have talked about the automatic voice alignment in that part of the Measuring Polyphony Editor, but I haven't talked too much about the editorial correction part. So what we wanted to know is if there was any way to facilitate the correction of your file once you have it in SCORE. If there was any way to facilitate the detection of these scribal errors. So for that, I work with Craig Sapp, who works on Humdrum, and we try to use these music analysis tools from Humdrum. Humdrum has a nice dissonant filter that what it does is that it labels the dissonances on a piece for you. So we integrated that into the Measuring Polyphony Editor. You can actually activate it in here. And when you activate that, what will happen with your score is that it will display some labels below, some in blue, some in orange. The ones in blue are the like well-known, or let's call them legal dissonances. Uh, so for example, here we have a few passing tones. You can see here a passing tone between these two notes, or between these two notes, etc. We have here a lower neighbor. We have here a suspension, and here it's resolving the suspension, and the agent of the suspension is marked here, for example. So all of that is marked in blue. Like, let's call them legal dissonances. And everything, other dissonances that are unclassified, they are marked in orange. And these are basically seconds and sevenths that are that don't seem to fit any functionality, and also fourths above the bass. And there are different types of unclassified dissonances. So, for example, unclassified dissonances, imparallel accompaniment, and all these kind of subclasses of unclassified dissonances. So those are marked in orange. So the idea was to test whether making these illegal dissonances obvious to the user help in any way in correcting the score. And we evaluated that with a subset of the pieces in another publication, and discovered that yes, indeed, marking the illegal dissonances reduced the correction time, because rather than going through this whole piece and find out why through all this piece what is messing up the alignment and why the notes don't end at the same time, you can just focus your search on basically all the notes preceding the first orange label. Yeah. So basically, this reduces your region to look for errors to just this part. Um, and let me see. So that reduces the amount of time for your search for errors. And in addition to that, it also increases the accuracy of your corrections because going back to the same example, you can see that the cadence following that first orange label, if you look at the cadence, you can see that it reveals that uh, this voice, the alto, has to be cut by a minim. It's a minim too long. So the reason why this can increase the accuracy using these labels is because if you test different solutions, you can see what happens with the orange label. So for example, if I take this rest and I cut it by a minim, uh, I will see that the labels following, the orange labels following disappear, but also a new one appears. So that's probably not the right solution. We can experiment with another thing. I already know the right solution, so I'm going to point it out. If you cut that semi-brief by a minim, then you can see what happens. The orange labels disappear, the cadence lines up, so that at least you gives you some hints. You can test your different solutions, and that increases the accuracy of finding the right solution. And other thing that we noticed was that surprisingly, marking illegal dissonances also helped detecting OMR errors that went unnoticed on the previous stage. Because we already had conducted the OMR, we have already corrected, and there were a few errors that went there, and we were able to detect them with this. So this is the work I did with Craig Sapp from Humdrum and Juliet Reginbald from the Measuring Polyphony project. Oh, by the way, the dissonant filter was developed both by Craig Sapp and Alexander Morgan. The attribution is on a previous slide. So, uh, all in all, the outcomes of this project, we're kind of still working on this project. My dissertation is done, but we're still working. I have a musicologist now check all the final pieces. But the outcomes consist on the digital images, which hopefully will be in DIAM, the mensural MEI files encoding both the separate parts and the scores. They are on GitHub, but we are still checking them. And also the workflow. This workflow presented here allows for the semi-automatic transcription of mensural music from digital images of manuscripts into scores in mensural notation. It's applicable to other mensural music sources, don't have to be only the Guatemalan corpus. So the workflow can be reused by other communities around the globe, uh, even the ones who have collections in need of preservation but have limited resources. Because I was trying for all of these tools to be as accessible as possible too. So these are DIY tools like the DIY book scanner that I mentioned before, and the software is free, online, and open. Um, so the other thing is that I want to emphasize that this project was trying to contribute to the development of research project that already exists rather to implement a monolithic tool that does it all. So it was contributing to each individual project and to their interoperability. And people always feel good when you reach out to them and say, "Oh, I'm interested in your tool. It's working pretty well, and I want to do this, and maybe put it together with this other one." So people get excited and get invested if they can. So, and it's better than just constructing another tool that might eventually just stop working if you don't follow through. So it's an example of bringing projects and researchers together for a common goal. Um, I wanted to show one of the pieces just so that you can see the outcome. Um, Let me see. So this is one of the triple meter pieces. Yeah, this is just the sanctus of this misa. Is actually the sonal movement of the sanctus of this misa. The title is a little bit misleading because it's not the whole mass. We don't see. Oh, thank you. So here is, I just uploaded it in. This is Verovio that is rendering it. It's MEI viewer, so you can go to that URL and upload your piece here. So I just upload one of the pieces, and Verovia can play it for you. So let's hope you can hear it. Okay, so that was just one movement of the sanctus of this piece. Let me change to my slides now. Okay. Um, so what I wanted to do with this presentation was to present you an overview of the tools that exist for menstrual annotation and how to put them together for a particular goal. There are tools that I haven't mentioned. So the ones that I mentioned here were two file formats: the Music Encoding Initiative, the Humdrum Men's format. I also mentioned the Verbal library for rendering these files, for rendering music, for rendering MEI. Uh, I mentioned some optical music recognition tools. I mentioned MuRET. There's another one, Arduspix. I didn't use Arduspix because this is for printed notation. It's also developed by Laurent Pujan, who developed Verovi. Also mentioned the Measuring Polyphony Editor as an online editor to enter and process menstrual annotation. I use it for its voice alignment or scoring up automatic functionality and its support for editorial corrections. There's another tool. This is more recent, MERIT, which also deals with interpretation of duration of the notes in menstrual annotation, but more from an analytical point of view. It's developed by Anna Flaxin and David Lewis. And I also mentioned the use of music analysis tools like the dissonance filter from the humlib library, which is one tool from Humdrum. Um, I want to acknowledge all the institutions and all the people that helped me in this large project of the digitization of the Guatemalan choir book. And I want to thank you all for your attention. These are my old email, still works, and my new email. So thank you.